Cool. So this week we're going to get more into graphs, a little bit more into trees, and we're also going to talk a little bit about physics. And so to kind of kick us off, let's talk a little bit more about graphs. And you probably have already some background in graphs and trees that, as we'll talk about it in this lecture. But you can never have enough background in this stuff. So to kind of go over this again, since you've probably seen this before, a graph ultimately consists of a set of points or vertices and also a set of edges, or effectively a pairing of points that are connected by a line segment. Keep in mind the mathematical definition of a graph. It's really a collection of of nodes, and also a collection of edges that connect those nodes. So whereas edges can be two items, any two items that are connected, the items themselves, the collection itself can be anything. In this case, we're probably going to be thinking about vertices for our graph, but it could be towns, it could be words. It doesn't really matter what it is. A graph is sort of this general purpose data structure that can be used for a lot of different things. So edges may have a direction associated with them, which is a directed graph. More often than not, graphs do have edge direction, but a undirected graph implies that every edge is sort of has its opposite, its conjugate. So if A is connected to B, then B is connected to A. But that's not always defined. So just keep in mind, most of the time when we're talking about graphs, we are talking about edges that have a particular direction. Graphs that don't have this association are what's called undirected graphs. So if you think about like a mesh, like a geometric mesh, like is in our use case, these are undirected graphs for the most part. Although you could argue that they're not undirected because of the way that we have to deal with winding the triangles and so on. So anyway, whatever. So here's a couple of examples of graphs. A graph doesn't necessarily mean that all nodes have to be connected to each other. In fact, some nodes may not be connected at all. And you might have a graph with multiple what look like graphs, but this is actually one graph. And also you can kind of have, you can include a line. So when you include a line, when you include an arrow in your graph diagram, that means that it's a directed graph, whereas when you don't include the line, that implies that it's a undirected or bidirectional graph. Graphs can have weights, so edges can also have weights associated with them. So if you imagine a map of cities, those cities have geometric distances from one another, but in a graph, this would be represented effectively with numbers, or the distance between these cities. So each edge would represent its geometric distance from that node from the other nodes that it's connected to. Here's another example of a graph. You can kind of see how this is effectively a grid, and we can kind of treat this as a graph where, say, you have an area in one quadrant, and trying to get to another quadrant, you can kind of map a line. So you can see which ones are connected to which, and you can kind of map a path between those nodes, which we'll talk about pretty soon. A little bit more terminology. So adjacency means that two nodes or two vertices in a graph are connected by an edge. So in the case of an undirected graph, A and B are adjacent to one another. But in a directed graph, keep in mind that if the A is connected to B but not the other way around, then B is adjacent to A, but A is not adjacent to B, because you cannot go to. So adjacent means this is connected to that, or that is connected to this, as in B is adjacent to A, meaning there's A to B. So it's a bit confusing with the terminology sometimes. And yeah, so if these two vertices are connected, they're adjacent. More terminology, a path is a sequence of vertices in which each vertex is adjacent to the next one. And that the length of the path is the number of edges in that path. Keep in mind that if there's a weighting, then you can basically map out the total weights of such a path. A simple path is a path where no vertex is repeated. A cycle is a path of that begins and ends at the same vertex, and this has to be more than one node, one vertex in this. So like a vertex can be connected to itself, but that is not a cycle. A graph with no cycles is called a tree, which I'm sure you can kind of imagine. If there are no cycles in a graph, then you're kind of guaranteed a tree-like structure. And a simple cycle is a cycle consisting of 3 or more distinct vertices in which no vertex is visited more than once along the cycle's path. So you can imagine like a circle, right? Like something that doesn't branch in that, and there's no way to create multiple cycles in that cycle. Oops, here we go. A little bit more, the degree of a vertex is the number of edges that it has to which it's an endpoint. So if you can imagine a point, a vertex with a bunch of edges, the degree is how many edges there are connecting to that vertex. And the neighbors of a vertex are the vertices that are directly connected to it. So these are the vertices that are adjacent to this vertex. A lot of this terminology is pretty like intuitive, so don't worry so much about knowing all of it, because a lot of it kind of makes sense, right? Like 2 vertices in a graph are said to be connected. If there's a path to one to the other, that makes sense. A connected component is a subset of the vertices that are all connected to one another. So this is if you imagine a graph, and inside of that graph you've got a number of fully connected vertices, then that's a connected component, like fully connected. And a graph is connected if there's a path from every node to every other node in the graph. A graph that is not connected is made up of connected components, effectively. When will it end? There's more terminology. A digraph, as we talked about, is strongly connected if for every pair of nodes there exists a path from one to the other. So this is almost like a complete graph, and an undirected graph is said to be connected for every pair of nodes. There's a path connecting the 2 nodes, meaning every node is connected to itself, to every other node. And this is the last terminology slide. So we are guaranteed to have no more than v times the number of vertices, v times v minus 1 divided by 2. That is the maximum number of edges that you can have in a graph with v vertices. So you can do the math to get here, but that's the number of edges that you can have. Obviously that's the maximum, so you're going to have somewhere between 0 and v times v minus 1 over 2. So when you have all edges present, meaning everything's connected to everything, that's a complete graph, right? Fully connected graph. Graphs with very few edges, meaning less than log v times v, these are considered sparse graphs. Graphs with relatively few missing edges, these would be called dense graphs. So a graph can have what's called an adjacency matrix. So the adjacency matrix is a one way to represent the set E, which tells you which nodes are connected to which other nodes. And they can be a Boolean like this. For example, you can see 2 is connected to 4. So if we look at the 2 row and the 4 column, there's a true there. Keep in mind that the adjacency matrix is a symmetric matrix, so its transpose is equal to itself. And this can be useful if you're doing manipulations on these matrices. Let's take a look at this graph. Feel free to pause the video and write this out yourself if you'd like. So this is what the adjacency matrix looks like. Again, you can kind of see in the case where you have a self-connected vertex, simply that point in the diagonal of the matrix is going to be set to true. So this is pretty general. If you think about this particular graph, first of all, you have a directed graph. So here, well, this is directed as well. Actually, I take that back. I'm sorry. Adjacency matrices are not necessarily symmetric. They're only going to be symmetric for undirected graphs. Because here you can see 4 is connected to 3, but 3 is not connected to 4. So there's a bit of a difference here. Wait. 4 is connected to 3. 3 is connected to 4. Yeah, they're not. It's not symmetric. Sorry, my bad. So the adjacency matrix covers the directionality, but you can see here, instead of using true and false, you can also use weights instead. So the adjacency matrix becomes a weighted. The booleans become values, and that way you can do a lookup on the connection, right? You can say, okay, well, no connection is 0, or something like that. I'm not sure what happens when you do negatives. That's a different subject. So one way to represent the adjacency list and this is going to come into play and when we start to kind of look at how to navigate these, right? For the adjacency list is a list of vertices that are adjacent to a particular vertex. So in this case, for example, 2 is connected to 3, 4, and 0. And you can see 2 has a list of 3, 0, and 4. The ordering of this doesn't actually matter. However, you may want to order them if you have weights associated with these edges. You may want to order them based on the weights, as we'll see in Dijkstra's algorithm, for example. Here's another example, right, where you have 0, which has a self. It's connected to itself, and 0 is connected to 0, 4, and 1. This kind of applies pretty generally where you have 3 in this node, which is actually not connected to anything. Things are connected to it, but it's not connected. So once you get to 3, we're stuck there forever. So how would we search a graph, right? We have to kind of ask a few questions about it. Is the graph connected? If not, where are the connected components? Do we have a cycle? The fact is, though, none of these issues for the algorithms that we're going to use actually matter. Because one of the things that we're going to do, it's a bit of a trick in a way, so we're going to ensure that we don't visit the same node twice. And so how we're going to do that. So there's a couple of different searches for graphs, although there are more interesting searches like Dijkstra's and A*, which allow you to find kind of the shortest path. So it's not necessarily to find a particular node in the fastest speed, but to find the shortest path between two vertices. We'll talk about first depth search and breadth first. And they both cover all the vertices, but they do it in a different ordering. So what you'll need first is a vertex class with data, right? And we actually need to have a Boolean attribute. And this allows us to keep track of whether or not we visited this vertex, because we don't want to search a vertex twice. It's just wasted time. Now, there's an alternative way to do this, by the way, where we maintain visited and non-visited sets, and we can kind of compare against them. So once we visited a node, we put it into the visited set, and that way we can make sure that we're not, every time we're looking and inspecting a node, we compare it to that. An alternative is to literally put this Boolean flag into the node structure itself and to have a wipe. And you can kind of see the different kind of benefits, pros and cons of doing it either way in terms of the performance cost, right? Where, doing the wipe, it's going to require us to iterate through this, and doing the set, we're going to have to iterate through it every time. So there's a lot of different ways to do this. So with the depth first search, it actually looks a lot like a tree-based search. So what we would do is we would add our root node to a stack. And there's a reason why we're doing this as a stack, by the way. And then we look at we pop the stack. So to start the algorithm, we choose a node and we start to search from there. And we pop the node off the stack, and we take a look at all its children, and we push all of those children onto the stack as well. And now we look at the next node in the stack. And we also mark A as visited, either by putting it into a visited set or by setting a flag on it, right? Then we look at the next node, and we push its children onto the stack, right? And while we do this, we also look at the children to make sure that those children are not part of the visited set or for using the flag. So for example, if B was connected to A in this case, right, because with the graph we can have that cycle, B would add E and A. But as we go through through the algorithm, we'd come across A and we'd say, oh, A has already been visited, skip. We won't do A again. So in that sense, we can turn this into a tree. Now we've added B, we've added E. E is not connected to anything. So then we're gonna pop E off the stack. We're gonna pop B off the stack already, if we've done that when we added E. And now we have C waiting for us, and we pop C off, we add F. We pop F off, now there's D, because we added it earlier with A. And D pops off, and then we add G, and then we're done, because there are no more nodes left. So that's sort of the solution. It's iterative, which is nice. This is not a recursive thing. So we pick, like I said, a vertex. We start there. We put that vertex on the stack, and we loop while we still have vertices on the stack. And that loop is effectively get the adjacent vertices. We push them onto the top of the stack. If there are none, no more, then we pop it off this. If we don't have any things, we pop it off the stack. We're done. But if we do, we push it in there. We flag it as visited, and yeah, that's kind of the idea here. So why does this work? Well, we are always looking at the top of the stack, and when a new vertex is added, it's pushed on top, so that becomes our current focus, and it moves us along a path each time and adds a new vertex when there is one. And if we don't have it, if we don't have anything to go, then it pops off, and then we're back to the depth that we were in before we pushed down deeper into that portion of the graph. And we don't process the same vertex twice in a row, or ever, because if we always check against that visited flag, we don't process vertices twice. So we're kind of guaranteed to only ever have one vertex on each one. And one thing this won't do, however, is keep in mind, if you have a graph with nodes that are not necessarily connected to the rest of the graph, it's not going to be able to determine that, right? We're not going to be able to sort of bridge to another portion of the graph. So if you have nodes with no connections, there's no way to get to them. One approach is to use what I was mentioning. You have a visited and non-visited set, right? And as you move nodes over from the non-visited set into the visited set, and you run out of connections, well, then you look at your visited set, you choose a point in random, you start off from there, and you keep rinse and repeat until your unvisited set is empty. That's one approach. So breadth first is actually exactly the same as depth search. There's not much difference between the two. In fact, we're using the exact same set of rules. The only thing we're changing is we're using a queue instead of a stack. And that's it. And well, let's talk about why, right? So when we use a stack, we're always looking at the top item, right? When A pushes B, C, and D onto the top of the stack, and then B pushes E on top of the stack and overwhelms C and D. But with a queue, what happens is we're kind of lining them up, we're queuing them up, right? So A queues up B, C, and D. So you go through B, and now you've added E, but it's at the end of the line. Then B pops off C, you add F, but it's at the end of the line. It pops off, now we're at D, it adds G, but that's at the end of the line. And now we pop off D, and now we have E, F, and G, because they have been added to the end of the line. And again, you're doing the same trick where you're flagging nodes that have already been visited as visited, so that we don't visit them twice. But also, and also you can always use the visited, non-visited paradigm using two different sets. It's just a matter of what you're trying to accomplish. So let's talk a little bit about Dijkstra's shortest path algorithm. And so say you have a node graph, a vertex graph that is weighted. And we want to find the shortest path between a point A, a vertex A, and some other vertex X in your graph. And so what this Dijkstra's will do is it will explore the graph and ultimately find the shortest path. And it picks the best solution based on the current data. Obviously cannot take into consideration future developments. And it's greedy, meaning it will only look for the best graph, the best path. It will not give you alternative paths, although you can kind of tweak it if you really want to. So a weighted graph, as we talked about, is a graph where each node, each vertex has an edge with an associated amount, like say the distance or how much money or whatever it costs. So everything has some kind of cost associated with it from going from one vertex to the other. So here's an example of such a graph where we have these different directional things, and that's actually really important for Dijkstra's, right? And we can talk a little bit. This is an example online. I recommend you guys check it out. You can use this to kind of step through the Dijkstra's algorithm, but we'll talk through it in this in a second. Here's kind of a view, like an animated view of this working, where you can see how it sort of incrementally explores what looks like a frontier and slowly gets to where it wants to go. It's a pretty cool little algorithm. So this is how we start. We actually start with an unvisited set, like we were talking about before. And we start off with each node being in the unvisited set and set with the shortest distance from the starting node. Now, how do we know what that shortest distance is? We don't. For all we know, it's infinitely far away. So that's actually what we start. We just use a really big number. A number so big that we're guaranteed not to hit it. And we start at the source node, and now we start to look at things one hop at a time. So we start at a source node, and we inspect all of its connected nodes. Once we've explored every connected or every adjacent node to that node, we mark that node as permanent. So we can do this with a flag, or we can take it out of the unvisited set and put it into the visited set, along with the shortest path that we've been talking about. And keep in mind, one of the things that's really nice when you use this, it's really nice to use priority queues or some kind of ordered data structure for the sorted and unsorted sets. That way, we're only looking at, especially in the unvisited set, we're only looking at the lowest values. So say we have a node A, like we have maybe 100 nodes, 100 vertices, and A is connected to 5 other nodes, and this one's connected with like 3 units away, this is 4, this is 1, and now we've updated the unvisited set with 1, and also the parent, which is important. We have to know which node we took to get there. If we have an ordered set, the shortest path away is going to be at the top. So once we moved our node into the visited set, now the next node we want to explore will be the one that's the shortest path away. You can kind of see this happening here, where it's going to kind of look at the shortest paths, which don't necessarily mean anything in terms of distances, because the weighting could be anything. But what you can kind of see happening is, because of that, it creates a kind of frontier versus just going down one path all the way until it terminates and then checking the next path. So using a priority queue or some kind of ordered data structure has a lot to do with why this pathfinding system really works well. So once we make it permanent, or we put it into the visited set, we continue to loop while there are any non-permanent nodes. So as long as our unvisited set has any number of nodes in it, we keep on doing this until we get to the there are none left. And what we do every time we visit adjacent nodes, we update the path length, right, from the source. So say at node B we're 3 away, and then node C is another 2 away from B, so C would be marked as 5, right, with its parent as B. What happens if we come across a node that we haven't that has a higher distance, well, from a different node, from a different parent? Well, we would overwrite the parent, we would overwrite the path to get there, and we'd set the new shorter path in exactly that way, and it'll be up again. That's how our priority queue, our unvisited set of priority queue nodes, will know which one to look at next. And yeah, so that way we can kind of ensure that we're updating our path based on the quickest route to get there, given all the other nodes that we're inspecting. And then we keep doing this until all the nodes are in the visited set, or the nodes in the visited set have all the nodes in the unvisited set have infinity, meaning there's no path to them. So keep in mind, you may have a graph where there's some nodes that are not actually connected to your main body of nodes. So you may be in a situation where your unvisited set has a bunch of nodes that are still set to infinity, meaning they've never been touched, and there's no way to get there, obviously. So there is no path to that node, and if your target path is in that unvisited set, where you can return that it's impossible to get to where you want to go. So yeah, you finish. That's when you finish. And when you want to get the actual path out of this algorithm, you can just read these labels, right? So each node has an amount, but also the parent that it took to get there, right? And so if you follow that effectively linked list from the destination node back to the source, it's just going to be a linked list to get back there, and you can push that into some data structure, or save it as a list, or what have you. But the algorithm kind of stays the same. So yeah, this is kind of an example, right? And say we want to get from A down to, let's say we want to get to F, right? So we start off at A, and you can see that we would then inspect B and D, right? D would be added with a length of 1, B would be added with a length of 2, and so based on that we would then go and inspect D next, right? D would then add F with a length of 9, because it's 8 plus 1, and then add C, which is going to be with a length of 3, because it's 2 plus 3. So for example, you can see from D to F, it's quite a long distance. It's actually 8. It's like the biggest graph there is here. And so, you keep iterating. So now we have C with a value of 3. Am I doing this right? Let me do it here, actually. So now we have C with a value of 3, and we have D with a value of 1, and B with a value of 2. So what that means now, B has now gotten up to the shortest path. We're going to explore B, and now B is going to add D with a value of 5, and E with a value of 12. Now, B doesn't actually add 5 to D, because B is going to look at D and try to look at, okay, our path is 5, but D is already in our, is already set with a value of 1. And so you don't have to update it, and so D doesn't get added again. So you can kind of see here where a cycle doesn't actually make it in to the thing. So our paths now are A to B to E, which is quite long, A to D to F, which is our destination node, but it's 9, and we have A to D to C, which is 3. So now C becomes the next destination node, the next node to inspect, and we add F to it. And F is now F is added 1, so 3, 8, and so that's shorter than ADF. So F is now updated to 8, and the parent is C. So we can get to F, A, D, C, F. Yeah, I actually didn't do this entirely correctly, because D also had G, and now it would have been the shortest path. But you get the idea. Sorry, I totally forgot that G was there. Ultimately, we would actually have A to D to G to F, and that would be 6. And that would ultimately win, depending on how you get there. So honestly, that path would consistently win until we do this algorithm until all nodes have been visited, which actually we would have done already after an iteration or so, and we would find our path. So yeah, sorry for the mistake there. So here's in the PDF, I recommend watching this video. It's quite good. And then also A star is it's a derivation of the Dijkstra's algorithm, and it's a little bit smarter about which direction to go versus using Dijkstra's, which Dijkstra will kind of go in whatever direction is available. It's not going to be intelligent about that. So yeah, recommend watching these videos as well. Cool.